Well, as you can see, this lecture is about antiderivatives and indefinite integrals. And it's really the beginning of our discussion of these things called indefinite integrals, or sometimes we just say integrals. And we'll be studying this for the entire chapter. But this is our beginning. This is our beginning to understand. And in the beginning, it will seem complicated. I assure you that. Because we're having to think backwards. So in the beginning it will seem complicated and we'll have to learn some rules, and every time we learn new rules it takes us a while to get used to those. But I assure you this will get simpler and simpler and simpler, like most things that we've done. Well, we first talk about this. Let's talk about these things called antiderivatives, and because that leads us to the idea of what an indefinite integral is. And of course, antiderivatives doesn't mean we're against derivatives. It's really the terminology for undoing the derivative. It's kind of going backwards. Decide what function we're looking at now, what derivative, what function that came from by taking a derivative. Now, here's what I mean. Let's start out this way. We say that the function, we'll call it capital F of x, is an antiderivative of the function lowercase f of x, provided that the derivative of capital F is what the lowercase function f of x is. Now, kind of an example of this, well, what am I trying to do here? The function, let's do this. The function capital F of x equal to x cubed plus x squared plus x plus 5 is an antiderivative of f of x equal 3x squared plus 2x plus 1. And the reason we can say that capital F is an antiderivative of lowercase f is because if we take the derivative of capital F, we get 3x squared plus 2x plus 1. And so that's the value, or that is the function lowercase f. So under those circumstances, capital F is called an antiderivative. Now, that seems like, where are we going with this? And that's true. The truth of the matter is what usually happens is we're given the lowercase f function, and we want to know what uppercase f is. We want to know what the antiderivative of lowercase is. So, for instance, let's just make a little table here. We've got a function lowercase f. Okay. And remember, uppercase f is the antiderivative. Okay? Antiderivative of lowercase. That's what that stands for. And so, suppose we're given the function 5x to the 4th as our lowercase function. In other words, f of x is equal to 5x to the 4th. So from that information, we want to know what an antiderivative is. And so what we have to recall for it to be true that capital F is an antiderivative, we have to remember that means if we take the derivative of capital F, we get lowercase f. And so the question ends up being, what function capital F exists so that when we take the derivative of it, we get 5x to the 4th? And clearly, I think you'll agree with me, that would be x to the 5th, wouldn't it? Because the derivative of x to the 5th is 5x to the 4th. So that it makes a lot of sense. And that's exactly what we're trying to do. Be given this function and figure out what this antiderivative is. But remember I said is an antiderivative. Does lowercase f, that is, does 5x to the fourth power, have any additional antiderivatives? Are there any other functions that we can take the derivative of that will give us 5x to the fourth? And I claim there is. I claim that, look, x to the fifth plus 1 is another antiderivative, because when we take the derivative of x to the fifth plus 1, we still get 5x to the fourth, don't we? And as far as that goes, I claim that x to the fifth minus 3 is an additional antiderivative. All three of these functions are antiderivatives of 5x to the fourth, because if we take the derivative of x to the fifth minus 3, we will get 5x to the fourth, won't we? So you might say, well, man, there's an infinite number of these, and you're correct. See, and in fact, if we have an x to the fifth plus some other constant, now I can't have an x in it, but any other number, x to the fifth plus any number will be an antiderivative, because when we take the derivative of x to the fifth, we get 5x to the fourth, but when we take the derivative of that constant c, we get 0, so the result is 5x to the fourth. Okay, well, this kind of summarizes this line right here, the entire family of antiderivatives. That is, it's symbolizing derivatives of our f of x equal 5x to the fourth. See, it's symbolizing that instead of saying, well, x to the fifth works, x to the fifth plus 1, x to the fifth minus 3, anything that's x to the fifth plus a constant will be an antiderivative. And so we're kind of summarizing the entire family. And when we discuss the entire family of antiderivatives, that's called the indefinite integral. So the indefinite integral represents the entire family of antiderivatives. Well, let's do one more real quickly, okay? And the real quickly is that let's suppose our function is x cubed. Okay, so that's our lowercase f. Now, what we want to know is what antiderivative, what's the antiderivative of x cubed? In other words, what's a function that we can take the derivative of that will give us x cubed? And now this became more difficult all of a sudden. But we know if we take the derivative of something and get a power of 3 that we had to start out with a power of 4, don't we? So we know that we have to have a power of 4 on this function. But the derivative of x to the fourth is 4x to the third power. And we need 1x to the third power. So we kind of, with a little fumbling around, we might figure out, oh, if we have a 1/4 in front of that, when we take the derivative, we'd say 4 times 1/4, which is 1, and our new exponent would be 3. So that will take care of us getting the x cubed part, won't it? But remember, the entire family of antiderivatives would be that amount plus any other constant, so any constant at all. So here again, we're looking at the family of antiderivatives, which we would call the indefinite integral. Well, let's go to the next page and see how we would call for this family of antiderivatives. Well, now that we have some idea of what an antiderivative is, let's see how, for instance, we have some idea of what a square root is. You know, for instance, the square root of 9 is 3. That when we say, well, what's the square root of 9? We're looking for a number that when we square it, we get 9, and so we figure out that's 3. But the call for, you know, we can speak it, but the call for finding what that square root is we use a special symbol, don't we? And so it's kind of the same idea here. The call for finding an antiderivative looks like this. Looks kind of like an elongated an S there, and that's actually called the integral sign. And so what we'll end up seeing is some feature that looks like this. Okay, that says more or less find the family of antiderivatives of the function lowercase f. Okay, that's what that's asking us to do. Now, of course, the answer will be that family of antiderivatives. Of course, they can all have a plus some constant. So let's kind of put this into perspective, what we just did a moment ago. A moment ago, I asked you to come up with the antiderivatives of, what was it? Oh, yes. We started out with 5x to the fourth, didn't we? So that was our lowercase f, that 5x to the fourth. And so what this symbol is asking us to do is find the family of functions, the family of antiderivatives, that when we take the derivative of those functions, or that family, we get 5x to the fourth. And we decided that was an x to the fifth plus that constant we see out there. Because after all, anytime we take this side and find a derivative, when we find, it's not the derivative, when we find the derivative, we get what's in here, don't we? See, we get what's in there. Well, let's talk about the pieces of this, because you need to be able to understand what I'm telling you. That symbol is called the integral sign. Okay, the lowercase f right here, okay, that function, oops, right here, that's called the integrand. That's what we're taking the integral of, or that's what we're finding the antiderivative of. So that's called the integrand, or we're taking the integral of. Now, this dx business that we see here, well, it's the x specifically, okay? It's the x specifically. That's called the variable of integration. All that's saying is that this function is about x stuff, not about y stuff, not about t stuff, not about z stuff. It's the variable of integration. Okay, the capital F here is what we were just talking about. That's called the antiderivative of. See, that is the antiderivative of lowercase f of x. And remember what that means. If we take the derivative of that function, we get lowercase f. And that's what this is really telling us to do. When we see the stuff on the right-hand side, see, when we see this, it's a call to go find those antiderivatives. And this c has a name for it also. It's called the constant of integration. And it's just what ties all those antiderivatives together, because anytime we have a constant and take its derivative, we get 0. So that just tells us that we have an entire family of these things. Those are the pieces or the components when we do this. And of course, the way it's read, so let me read this to you one more time right there. That first symbol, we say the integral of 5x to the fourth, and then that dx we read with respect to x. The integral of 5x to the fourth with respect to x is equal to x to the fifth plus c. And so what we're after in this section is to find what is it equal to. See, it's this part we're actually trying to find. So we're going backwards, and that takes a little bit of getting used to. Now, there happen to be 4 basic rules of integration. In fact, they're pretty much the rules of integration. I call them basic. And what I'm going to do is write them down all together right here, and then we'll go back and look at examples of each type. So the first basic rule is the integral of a constant. So k just represents a number. So there's no variables there. The integral of a constant with respect to x is just that constant times x plus a constant of integration. Now, another separate constant. And again, we're going to come back and look at these individually, but I want to get them all out in the open right now. A second very powerful rule and tool for us is the integral of x to a power. Okay? X to a power with respect to x. So n represents an exponent. Well, what that happens to be is the fraction 1 over the original exponent added 1 to, okay? And then times x to the power n plus 1. So we're taking the original exponent n and we're adding 1 to it for the denominator of a fraction and also as a new exponent, plus our constant integration. Now sometimes, and our book will do this, I just don't, okay? Sometimes this is written as x to the power n plus 1 divided by n plus 1. And I just don't prefer that, but they're equivalent, aren't they? Now there's one thing that we have to say here. There's one little extra piece of information. This rule works as long as n is not equal to -1. See, if n was equal to -1, we would have a fraction that had a 0 in the denominator, wouldn't we? N plus 1 would be -1 plus 1, which would be a 0 in the denominator. So that rule only works if n is not equal to -1. Now the third, or a third, that don't have to particularly be in an order, is the integral of a constant, not alone, a constant times a function. Okay, it's going to take us a while to see where all these fit together. But the integral of a constant times a function, well, the way we can calculate that, basically, is we can factor the constant outside the integral sign and then just find the integral of the function itself. So it kind of makes us, puts us in a position where we can find integrals by taking one little step at a time. And then the fourth rule has to do with what happens if we're integrating things that are added together. So for instance, the integral of f of x plus a second function g of x with respect to x. Well, the way we can approach that is we don't have to worry about the big problem. We can think about it as two different integrals. That is, we can find out what the integral of f of x is and find out what the integral of g of x is, and then add those two results together. I put it for plus, but it could also be for subtraction. Okay, and in the case of the subtraction, we'd have a subtraction over here between the integral signs. So those are the four basic rules, or the four rules of integration or finding antiderivatives. And now what I'd like to do is go through each rule and look at some examples. And then we'll put all those rules together to get to be able to do more and more complicated integrals. Okay, back to the first rule, which is just the integral of a constant. So I've written the rule here. The integral of some constant with respect to x is that constant times x plus another constant of integration. So let's see how this shows up. Let's see how we would look at this in practice. So it might be like the integral of 3 with respect to x. So it might look that way. So the k is our 3. Well, what this tells us by rule is that result would be that constant times x plus a constant of integration. And so the claim is then that if we take the derivative of this right side, we get what's in here. We get that integrand of 3. And of course, yes, the integral of 3x is just 3, plus the integral of c, which is a constant, is just 0. So when we take the integral of the right side, we in fact do just get 3. And so now you kind of understand why this rule works. If you take the integral of a constant times x, you just get the constant. Okay, so it makes sense then. Now, I need to mix in a little more information here, because sometimes our variable is not is not x. So for instance, if we had the integral of, say, -4, and then we had a dt here instead of a dx, then that's telling us our variable is t and not x. So it would work the same way, but we wouldn't be using an x. That is, we'd use a t instead. So it would tell us that, the result will be that constant times the variable, which in this case is t, plus the constant of integration. And so, yes, the derivative of -4t plus c, if we take the derivative of that with respect to t, we do get -4, don't we? Okay, let's look at another example here. The integral of 1/2 with respect to x. Well, according to this rule, that would just be 1/2 times x plus this constant of integration. And once again, clearly, the derivative of 1/2 x is just 1/2, isn't it? And of course, the derivative of c, being a constant, is just 0. So when we take the derivative to the right side, once again, we just get 1/2. We get the integrand. Remember, the derivative of this entire amount has to give us that value that's right there. Okay, one last example, just because I don't want it to sneak up on you and you be surprised. The integral of 1 with respect to x. Well, according to this rule, that's just 1 times x plus a constant of integration, which we would just normally write as x plus a constant integration. And again, we see this is clear. The derivative of x is just 1, isn't it? Now, the reason I'm doing this, one, so we won't be surprised by it, and two, occasionally you see this written a little differently. See, occasionally you'll just see the integral of dx. Well, remember that really we could write as the integral of 1 times dx, couldn't we? And so we in fact get x plus c here, and in other words, these two are interchangeable. And so if you ever see this, you'll know what we really mean by that. Don't be too surprised then. Okay, remember this, the second rule is actually called the power rule. The first rule there is called the integral of a constant. Second rule is the integral of a power. And so I write that rule down. It says the integral of x to the n with respect to x. Remember, it is 1 over n plus 1 times x to the power n plus 1 plus our constant of integration. Separate these, if you don't mind. And that's true provided, the rule works provided n is not -1. Okay, so let's look at several examples here. We need several examples. The first example, we want to know the integral of x to the third power, for instance, with respect to x. The integral of x to the third power. I think we did this one in the very beginning, except we just had to think it out. But this tells us, here's the way we can do it. And let me show you what I would do. I wouldn't worry about the fraction part. Here's the way I think about this. Let's first worry about the exponent, the new exponent. And what this rule says is when you're integrating, you go backwards from differentiating, don't you? When you find a derivative, you decrease exponents. But when you find an integral, you're going backwards, so you increase exponents. So it tells us the exponent on our answer has to be 1 more than the exponent we started with. And then we have to offset that, basically, with a fraction, because, and we'll talk about that here in just a moment, and that fraction is 1 over the new exponent. So that kind of helps me remember how to do this, plus our constant of integration. But now we can simplify that as 3 plus 1 is 4, so that's 1/4 times x to the power 4 plus our constant integration. And then it becomes clear why we have that 1/4. Because when we take the derivative of this side, we're going to bring that exponent down, and if we didn't have that 1/4 there, then we would just get an answer of 4x to the third power. But we need 1x to the third power. So we had to have something to multiply that exponent with that would offset that multiplication, and that's the reciprocal of the exponent. So now it makes sense why we have that fraction out in front. Okay, well let's do another one here. The integral of, say, x to the 12th power with respect to x. Okay, now let me again tell you how I'm going to approach this. I'm not going to just look at the rule only, because if I'm just memorizing rules, it never fits together. So the first thing I'm thinking is that if I'm integrating, I go backwards from differentiating. So I'd have to add 1 to the power. So that tells me my new power is 13, 12 plus 1. And then what I remember is that the fraction that goes in front of that actually has to be the reciprocal of the power. See, up here, that 1/4 is the reciprocal of the new power 4. So what's the reciprocal of this new power 13? 1 over 13, isn't it? And then don't forget our constant of integration. And then we could double check the derivative. That is, we could find the derivative this side, and if we find the derivative and we get x to the 12th, then we're correct. And of course, when we find the derivative, we'd say 13 times 1 over 13, which is 1, times x to the power 12, because we decrease the exponent. So we would get 1x to the 12th plus 0, or just x to the 12th. So that does check out, doesn't it? Okay. Well, it's not always going to be so easy, okay? And here's the next thing we have to worry about, that this power rule that we're looking at right now can be needed when it doesn't look like anything that we've seen before. It's kind of like we did with derivatives. Suppose we were asked to find the integral of 1 over x to the 3rd power. Now, if you look at our rule, it has nothing to do with fractions, does it? It's just the integral of x to a power. And so you have to be careful that we can't apply this power rule when we're looking at this integral the way it is. So this is similar to what we might have done when we were dealing with derivatives. We first have to write this in a form so our rule applies. And that form would be, let's not write it as 1 over x to the 3rd power, let's write it as x to the power negative 3. Now we do have x to the power. And the rule didn't say we couldn't have negative powers. It just said we couldn't have a power of negative 1. So our rule will now apply, and so to apply the rule, what do? We increase the power by 1, don't we? See, I'm thinking we're going to have x to a new power. And so I'm coming over here and I'm thinking, well, what is that new power? It's negative 3 plus 1 more, isn't it? See, we increase the old power by 1. And so that gives me a negative 2. So I know this power is going to be a negative 2. But remember, we also have to offset that new power for going the derivative way. And so we have to create a fraction in front of this that's the reciprocal of that new power. And that new power is negative 2, so its reciprocal is 1 over negative 2. And then we can't forget the constant of integration. Now, we'll probably clean this up a bit. In fact, we'll clean it up quite a bit. Let me tell you the 2 things that we would do. First, we'll write that 1 over negative 2 as a negative 1/2. And this might be a good time, okay? Well, I'll come back to that. And then we normally, see, the problem wasn't presented with negative exponents, so it's probably a good time at this stage to rewrite x to the negative 2 as 1 over x to the positive 2 power, okay? And then we can do one more step of simplification here, because these 2 fractions could be multiplied together, and we'd get negative 1 over 2x squared, wouldn't we? So this is the integral, the indefinite integral of 1 over x cubed. It is negative 1 over 2x squared plus a constant of integration. Now, that's our answer, and since I've run out of room here, I'm going to steal this extra space. You know, how would we check to see that we're right? Well, the way we check to see that we're right is we take the derivative of our answer. Whoops. So there's our answer, and we find that derivative. Now we know that the derivative of a constant is 0, and so this is the same as just what's the derivative of negative 1 over 2x squared, isn't it? Because plus the derivative of c, which is 0. So if we take this derivative and we get 1 over x cubed, what we started with, we know we're right. Well, what we have to do here is we have to think of this, we can go backwards as we did before, that this is really negative 1/2 times 1 over x squared, or negative 1/2 times x to the negative 2 power. I haven't taken a derivative yet, but that's what we're taking the derivative of. And so in that case, I would have my negative 1/2, I would multiply with my negative 2, and I'd decrease the exponent by 1 when I take the derivative, so I'd get a negative 3. And you can see negative 1/2 times negative 2 is positive 1, and so I get x to the negative 3, which is 1 over x cubed, isn't it? And so when I take the derivative of my answer, I get my original integrand. When I take the derivative, finding derivative this direction, that tells me I'm right, because after all, that's what an antiderivative is. Okay? Okay, let's, I've got a couple more examples here that I like to use before we move on to the next rule. Okay, continuing with this power rule, we might be asked to find the integral of x, the integral of the square root of x with respect to x. And again, this is kind of like when we were dealing with derivatives. We had a rule for finding the derivative of a power of x, but we didn't have a rule directly with finding the derivative of square root of x. And it's the same thing here. We have an integral for finding the integral, a rule for finding the integral of the power of x, but not a rule specifically about finding the integral of a square root of x. But the issue is that we can write square roots as powers, can't we? So when we use a little algebra and we rewrite our problem, then we recognize this is the integral of x to an n power with respect to x. And so let me remind you of what our power rule is over here, okay? It says the integral of x to the n power with respect to x is 1 over n plus 1 times x to the n plus 1 plus our constant of integration. Now remember, what I've been doing is I've been figuring out that exponent so I know what this fraction looks like. So what this would tell us generally, though, is that the fraction we're going to have in front is going to be the old exponent plus 1 more. And the new exponent is that same thing as the denominator. The new exponent is the old exponent plus 1 more. And then we can't forget our constant of integration. So we need to come over here and figure out what this new exponent is. That is, the old exponent plus 1 is 1/2 plus 1. And of course that's 1/2 plus 2 over 2, which is 3 over 2, isn't it? So as I come down here, then that ends up being, let's see, this denominator, 1/2 plus 1, is really 3 over 2, isn't it? And the exponent we have, 1/2 plus 1, is really 3 over 2. And then we can't forget their constant integration. Now, we have a little bit more of an issue here, is that with this fraction, this has a fraction in it. So let's remember what that means. If we have 1 over 3 divided by 2, doesn't that mean what we're dividing into times the reciprocal of 3 divided by 2, which would be 2/3, and so that's just 2/3, isn't it? So this fraction in front simplifies to 2/3 times x to the 3/2 power plus our constant integration. And let me stop here for just a moment, because what I want to tell you now how I would do this a little shorter. and you can look above and see why I'm doing the steps that I'm doing. So I'm asked to find the integral of the square root of x with respect to x. So I rewrite square root of x as x to the power 1/2, and that's all I've done so far. Now I know when I get my answer, I'm going to have x to a new power, and I'm going to have a fraction in front of that. Okay? And then I'm going to have this plus constant out here. And so I'm trying to figure out what goes here and what this exponent is. And I know the exponent, that's what I'm going to concentrate on. I know the exponent, I go backwards from taking derivatives. So I take the old exponent and add 1. And we just saw a moment ago that that was 3 over 2. So I know this new exponent is 3 over 2. Okay? So that's what I concentrate on first. And then here's what I know the fraction is. See, 1 over the new exponent, when I say 1 over the new exponent, that's the same as saying the reciprocal of the new exponent. Well, when the exponent is a fraction, then the reciprocal is flipping that fraction, isn't it? So that tells me immediately when I know my new exponent's 3 over 2, the fraction's going to be 2 over 3. And that way I don't have to go through that 1 over 1/2 plus 1 business. That makes it a lot easier to deal with. Now, let me reiterate the way we would check to see that we had done this right. I'm not going to go through the steps, but to check our answer, we would take the derivative of our answer. And so what was our answer? 2/3 times x to the power 3/2 plus a constant of integration. And when I say check, what are we checking? We're checking to see that if when we take the derivative of our answer, we get our original integrand, what we were taking the integral of. And in fact, if that derivative gives us the square root of x, then we're correct. If it doesn't give us the square root of x, then we're incorrect. And so I'll leave it to you to check on this particular example. Now, I would like to kind of leave here with one more thought, and that will be the end of part 1 of this, and then we'll go to part 2 with new rules, or the additional rules. And that is this, that if we're asked to find the integral of 1 over x with respect to x, see, if we approach this like we have done in the past, we could write that as the integral of x to the negative 1 with respect to x. And then if we try to apply the rule, then what we would end up with is, let's see, our new exponent would have to take the old exponent and add 1, and that would give us a 0 exponent. But remember, we'd have to have the reciprocal of that exponent, and that would be 1 over 0, and then we'd put the plus constant here. But that's an issue, isn't it, right there? And remember, in the very beginning, we said the power rule doesn't work if our original exponent's negative 1. And that's the reason it won't work, is because it creates a fraction that has a 0 in the denominator. So for now, we don't know how to do this. We'll come back and talk about that later, but we don't know how to accomplish this. There is a way, but the power rule is not the way. Okay, well that ends the part 1 of this section. We'll continue with part 2 and maybe part 3 in the next video.